All right, so continuing on categorical data, we'll finish up. We're going to look at categorical data today with visualization. At any rate, for before we change topics, try to get up into a little higher dimensionality. Categorical data. So last time we looked at tables and fooling around with tables and what you can do with tables, and also again a look at the Eikosogram. In that long sort of example of going through the Monty Hall problem, et cetera, hopefully gives you some idea of what an Eikosogram is and how to interpret it and how to reason with that. Because now we're going to use thinking about models that might produce cross-classified data and viewing them through Eikosograms and some other visualizations that are related. So let's just look at this Eikosogram. Remember when we were introducing it, one of the interesting things was that flatness kind of indicated independence. And so just remind you again that we have here cross-classified data, 4 values of the x or horizontal in this case, and 3 values for y. And the width of the bar at the bottom is the marginal probability of that value of x. And the height of any bar within that group is going to be the conditional probability of that value of y given that value of x. Okay? So, knowing what you know about independence, independence is simply stated as, if I think about the probability of y taking some value given x has already taken a particular value, if that probability does not depend on the value of x at all, right, it's just the same as the marginal probability of y taking that value, then x and y are somehow independent. Particularly, they're independent for those particular values, but also they're independent for all values, provided that holds for all values of little y and little x. And if you have one, you have the other way around, because of Bayes' theorem, going to get you so that equivalently the conditional probability for x given y is going to be the same as the margin. And that's what's happening here, so that this height of this bar at any point is the same height, whether x is equal to x1, x is equal to x2, x is equal to x3, x4, right? So that's certainly all independent, and it's true for every value of y. So we see these parallel bars here. So when I see that, all of them parallel like that, I'm thinking that that's clearly evidence of independence. That is the definition of independence, since these embed the probability laws in them, right? Okay. Everybody see that? And turning that around, this is the same joint distribution, but expressed in terms of the marginal probabilities of y and the conditional probabilities of x given y. And those areas have to match. This bottom left corner area has to match that bottom left corner area, wherever the x's and y's match. Okay. So the nice thing about an Eikosogram is independence smacks you in the face if you see flat features, okay? So it's a nice way of telling independence. You'll recall for continuous data, we had that when we looked at ranks. When we look at the ranks as a scatter plot, the fact that they look like uniformly distributed points would be indicative that they would be independent. So now you've got that for continuous data, and here it is for 2 categorical variates. And it's simple to think about this just in the binary situations. And so again, binary, two values of x, 2 values of y. You have independence if you see either one of these Eikosograms being flat. If one of them is flat, the other must be. Okay? So what I want to do is use that to think about a lineup test. And to think about a lineup test, I want to go back to the table of counts. So here we've got the table of counts, and I'm using Nij to be the ith row in the jth column, the number of values in that cell. So I've got the x's along the horizontal. The j goes from 1 to capital J, and I've got the y's along the vertical, and they go, the yi goes from 1 to capital I. That's a capital I there. It looks like an L. Capital I. And I've arranged them from 1 to capital I, going in increasing order of the index, just to match the Ikosogram. So using this notation where I've got a plus, that means I've summed over that index. You can see that the row totals over here are going to be summing over the second index all the way along. The column total is summing over the first index, and the grand total is summing over both indices, which can be the sum of that or the sum of that. So from this table, we could estimate probabilities that represent the joint distribution of this collection of numbers. So we think about what's the marginal probability that x takes value x1. Well, this bottom row is giving us some information about that, right? So I might estimate the probability that x equals x1 to be the total number of values that, total number of occurrences where x is equal to x1 divided by the total number of occurrences overall. So these guys divided by the grand mean are going to be estimates of the marginal probability, right? Similarly, these row totals are going to be estimates of the these divided by the total are going to be estimates of the marginal probabilities, the values of y, taking the various values. Now, conditionally, given that I'm looking at x equals x1, right, I would be estimating the conditional probability that y takes value y1 just by that count there divided by that total. Right? Make sense? So I pretend that I'm just looking at this column all by itself. There's a total of n plus 1 values there. If I'm guessing what the probability is, this would be the maximum likelihood estimate if this were a multinomial probability, right? Estimate what the probability that y takes on value y1, it's going to be how many did I see in that condition divided by the total number of values available that all have x equal to x1. So this over that was going to give me the conditional probability of y given x, and I can do it for given x equals x2. It could be a different conditional probability. For x equals xj, a different conditional probability. Similarly, this way, I can do the conditional probabilities for y taking any values, for x taking any values given y is fixed. So given y equals y1, y equals yi, n capital I1 divided by n capital I plus is an estimate of that conditional probability. And similarly, these ratios all along that way. Okay? And that should make sense to you if you think about how would you estimate the joint probability of any one of these. You'd say if I wanted to do for the P22 cell, the 22 cell, I'd think about, I could take the marginal probability of getting x be equal to 2, so that n plus 2 divided by n plus plus, times the conditional probability of getting y2, right? Given that I've got x equals x2, which would be n22 divided by that, multiply those, and I'm just going to get n22 over n plus plus. So that's exactly as you would have guessed. So that's how the probability is going to work, and those relate entirely to the Ikosogram. So everybody got that notation? That's all familiar, right? Good. So a little dancer slide here, but it says essentially what I've just talked about, but now we're going to look at unconditioned that they're independent. If they're independent, that conditional probability, every conditional probability can be replaced by the marginal, right? And that means that my estimate now of any ij cell should just be the product of the marginals. So that's what the model is imposing, okay? So let me just go back here. If I took this n22 case again, and if I assume x and y are independent, then my best guess of what the probability that y takes y2 is, it's going to be n plus 2 over n plus plus. And the probability that x takes value x2 is going to be n plus 2 over n plus plus. I'm just going to use these marginal things and multiply them together to get my estimate of what that probability should be, assuming independence. Okay? So that should be familiar as well, which means we can take any collection of numbers and impose this independence on them if we're interested in exploring that possibility. So if I want to think about a lineup and I want to assess whether or not the categorical variates I'm looking at appear to be independently distributed, what do I need? I need the Ikosogram for the data and also the Ikosograms under the hypothesis of independence, which means I have to generate data under the hypothesis of independence. Okay? So what this is about then is how might I generate that data? So, for example, if I think about the Ikosogram where y is conditional on x, so y is on the vertical axis, x on the horizontal, what I could do is I could fix the values of each x, right? Hold those numbers constant. And then I just need to generate y values for each one of those constants according to the probability vector that corresponds to the marginal probabilities of y. Okay? Make sense? So if I have that, I know how to do that. I can generate from a multinomial distribution. I can just get some counts given those probability vectors. So now, for fixing the totals of the x's, I can generate new y counts for each x from the same distribution, the same multinomial distribution, because the x shouldn't matter. All it's fixing is the total number of counts. Okay, so that's one way of doing the generation. We'll call that the conditional way. And the condition is that I'm not changing the x's, not changing how many x's are in each category. Alternatively, I could do this unconditionally, and what I'll do is I'll first generate how many x's go in each category. I'll do that using a multinomial based on the sums across all rows, the column sums, right? And say, let's take the total number that we have in the data set, the total number that we have in each of the x slots, use those to produce a probability vector, use that probability vector to generate new numbers of each value of x that sum to the same total. Okay, so I just generate the new collection at the bottom here. I generate that first. Once I've generated one of these, I can proceed just as before as the conditional. I can generate the y's for that fixed thing. Okay, so the conditional thing is fix these guys to be whatever they are in the data and just generate these according to these proportions. The unconditional says, first, let's generate these totals according to these proportions that I see here. I'll generate the totals. So there's going to be some randomness there. It'll be a multinomial. Then once I get those new totals, generate these exactly as I said before according to this marginal distribution. Okay, so two ways I could do this. Everybody with me? All right, so that's what all that does. So let's figure out how we're going to do this. So I have to have some code that'll generate a table. And it's going to have I need the two-way two-way table that I'm working with, identify which one is the response, which one is the conditioning variate, and whether I want to do that conditional test or that unconditional test. So this last thing is just a flag that's going to make, it's for you to choose between which one of those ways you want to generate data. Okay? So most of this is going along to get the information about marginal probabilities for the y and marginal probabilities for the x, for the rows and the columns. And then if I'm going to use the conditional test, I need to generate new totals of each column. And now I'm going to go through and generate for whatever those totals are, right? So if I've generated, if I have the conditional test, I'm going to use the totals that are in the table. If it's unconditional, I'm going to generate them, okay, using those same proportions, Q. And however I've got these now, the generating the conditional part is the same. So I'll take those values. These M is now the totals of each column, and I'll go and generate new values here, new response values, new counts, just using that multinomial with however many I have there, and that the marginal probability distribution for Y. Okay? So that looks a little complicated, but it's not really. It's just that simple that we talked about. So generate that new table and return the new table. And what we're going to use is an Eikosogram to assess the independence. Now the Eikosogram, the current implementation, is grid-based. In particular, it's presently ggplot 2 based, but that's going to change to just be plain grid in the next version. And that means I have to adjust my lineup function slightly. So lineup, remember, lineup doesn't care about anything. You've got some way of getting the data, giving me the data. You've got some way of showing the suspect, some way of generating the suspect, etc. And what I have to do is nothing there. That's the same as we've had before. And where it happens here is I have to find out what package are we using to draw the graphics. So there's an extra argument there about the graphics package. And if it's the base graphics, I'll do the layout as I did before. I can use these par parameters and lay out the plot. If it's not that way, I have to use that grid graphics. And you'll recall from your grid graphics, you're actually controlling a lot of where you place stuff. And the grid graphics have graphical objects called grobs, just that short for it. And I have to arrange those. So it's slightly different functions I have to use to do that layout. Okay. And excuse me, at the end, I'm going to return the true location, and the plot layout will be on a component of this list. So working with the South African heart data, and I'm going to look at the relationship between whether you've had coronary heart disease or not, and whether there's family history of heart disease. So we've built that table before. I'm going to need to have a new kind of data set. So I have to have a table, and I have to know which is the response variate, which are the conditioning variates that you're going to be using, and therefore adapt these generating functions that generate the data, either conditionally or unconditionally, depending upon one for each, because the lineup has to be given a particular choice, and they're both going to call this generate table, which we just wrote, and they're going to return this fancier data structure. Okay, just whether or not they have that last argument true or false. So almost there. So we need a show table. So I've got the data and the suspect. I've got a result, and I'm going to call the EIkos on this with all of the pieces that we need, turning off lots of labels and legends and things, so it's as simple as possible. And now the lineup test looks just like it always did. I can call the lineup on our data with the generating and showing functions that are appropriate and the layout that I want. Okay? So, any questions on that? So you understand how we're going to generate them, you understand that this is just a slight extension of what we've seen before. Okay, so here they are. Family history, and this is the conditionally generated test with, let's just go back, I forget which was which. Where's our data? Our response is the coronary, and the conditioning variate is family history. Okay. So, question. Which of those would you choose? Independence is going to be flat. And because we've got data here, there's a random generation, we're not always going to see flat things, even if they are independently generated. So what we're looking for is the least flat looking Eikosogram. Okay? Which shouldn't be too hard to detect. I imagine everybody's going to pick that one. that's the right answer. So evidence against the hypothesis of independence immediately just from these displays. The unconditionally generated test, this looks fairly similar, but what's different is, you'll notice, for example, here, that the number of x's in each one of these things is not the same. In the last one, all of these guys lined up. So that's the conditioning. I'm holding the x fixed. This is unconditionally. The x can be vary according to a multinomial based on those margins. Again, anyone want to pick one here? Yep. Number 12. Yep, this one here. That's the answer. So definitely evidence against the hypothesis, even unconditionally, of independence. All right, so we don't believe these two variates are independent, as evidenced by this data set and this test. Any questions? Okay, so you can now have a test, a lineup test for testing independence of categorical variates, at least for two variates. That's fairly straightforward, and that'll work. You also have a lineup test for doing it for continuous variates using the ranks. We just didn't build one, but you could build one, right? So what else can we see here if we're trying to model dependence and independence? Well, not only can you see independence or not, you can actually see the nature of the dependence. That's also true for looking at plots of ranks, but it's a little more complicated because usually the models in there involve things called copula models to try and look at ranks to determine the dependence. But here it's fairly straightforward since it's all just multinomial things happening here. So many things that you can see with a icosogram that you mightn't see, say, with Venn diagrams or other things, are these things that we had taught you to worry about in Stat 230. Independent events, we've already seen things that are independent. When are they coincident? What are mutually exclusive events, right? If you think about how you might draw a Venn diagram for mutually exclusive events, or how you would draw a diagram for independent events, one of those is really easy, the other's not. And people often draw the same diagram to non-intersecting circles for both of those, and one of those is quite wrong. Okay? So the icosogram has the advantage of being able to distinguish all of these things just by having a look at it, and to see whether there's positive association in the sense that given one event happens, the other is also more likely to happen. So here we have on the left, we have coincident events. So imagine you've just got an event that happens, yes or no. So if X happens, the probability Y happens is 1. Yes, it must happen. If X doesn't happen, the probability that Y happens is 0. X and Y are coincident. They both happen at the same time, or they don't happen at the same time. They're coincident events. Mutually exclusive, one of them can happen and the other can't happen. That's the other side of the bar here. So if X happens, Y does not happen, cannot, has probability 0 of happening. If X doesn't happen, Y has probability 1 of happening, right? They're in fact not just mutually exclusive, they're complementary, right? If X happens, Y cannot. If X doesn't, Y must. Complementary events. So we can think about an association. The association is that, let's look at the positive. If X happens, Y happens with high probability. If X doesn't happen, Y happens with low probability. Conversely negative, if X happens, then Y happens with low probability. So it's less likely to happen if X happens. It's more likely to happen if X doesn't happen. This bar is higher than that bar versus that bar is higher than that bar. Okay, so the size of the bars is giving you some sense of association, relative heights of the bars. And you can see this transition from these complementary events over here, mutually exclusive events on the left, to a negative association to independence to a positive association to coincident events. So all of those ideas that you saw in 230 just sort of map very trivially to an Eikosogram with a pair of events. Any questions? So a lot you can reason about with these things. Let's just look at some data. So here's a classic table that we've looked at before, survival on the Titanic. And it's got many more variates than just the two. But we can look at a bunch of questions about, does survival depend upon the sex? So calling Eikosogram with that, with survival as the response, sex is the conditioning variate. Does it depend on the age of the passenger? Does it depend upon the class of the passenger? And if there's no dependence, we're looking for something that looks like a flat Eikosogram. Okay, so first one. Does survival depend upon sex? Or are they independent? They're not independent, clearly, right? If we ran that through our lineup test, almost certainly we'll find that picture. If you're male, you're much more likely to not have survived than if you're a female. Okay? There are children and adults. If you're a child, it looks like it's close, 0.48, close to 50% chance that you would have survived. The surviving is the good one on top, or not survived. If you're adult, you're much less likely to have survived. So we just saw women and children first, right? The famous quote. Class, again, you can see that this is not flat. Your survival rate depends upon what class you were on that boat. And again, the survival rate is, the good part is the gray, so you're most likely to have survived in the first class, less in the second, less in the third, and less in as a crew member. And you can almost see an association going on there as the class increases in number here. If we think of the crew being fourth class, the probability of survival decreases, or the probability of dying increases. So you see that kind of association. Everybody, any questions? Now let's move up. 3 variates. Okay, so now I've got an X, a Y, and a Z. They're all binary, just to keep things simple. And these are all representing the same thing depending on what's the response. The response here is Y, here it's X, here it's Z. They take value yes and no. So on the left, what do I see here? I see that these two boxes together, that's when Z is yes. These two boxes together is when Z is no. This leftmost vertical strip is when X is yes and Z is yes. Next one is when X is no and Z is yes. You notice that these two are flat. That says that conditional on Z being yes, X and Y are independent. Conditional independence. Right? Conditional independence is something you'll see in a lot of modeling, particularly graphical models, so-called Bayesian networks, etc. Very important concept. Okay. It's also true that if Z doesn't happen, Z is no. Whether X is yes or no, the probability of Y being yes is the same, so it's also independent there. When I see that flat there and that flat there for every value of a Z, then I'm saying Y is conditionally independent of X given Z, generally. Okay. And that might manifest itself in these other pictures here. So if I have X on the vertical axis, you'll see Z is yes on the leftmost and the third one in. So those are the same height. It's a little harder to detect the flatness there. And similarly, those are the same height. So that's reflecting the same conditional independence. But notice if I had Z on the vertical axis, it's going to be really hard to see that conditional independence in that plot. There's no flat structure there. Okay? So you almost have to look at every one of these guys on the vertical axis to see which one is exhibiting conditional independence, if any. Everybody understand the conditional independence? It's the same thing as independence, it's just you've got one more thing that's being conditioned on in every probability statement. Okay? So you can see lots and lots of different patterns of behavior here. So here's another distribution, three-way distribution. So we got a conditional independence here, conditioned on the value of Z, right? The Y doesn't depend upon X. Same here. We've got a conditional independence here of conditional on the value of Y. Z and X are independent. And I've got this all flat here. So here's the worrisome thing. You might see this entirely flat and say, oh, that's great. They're all independent. And what we have is they're all conditionally independent here in that X and Z are conditionally independent, Y, X and Y are conditionally independent of Z, and Z and X given Y, and Y, same thing there, Y and X given Z. But there are a couple of conditional independencies that don't hold. That is, if I condition on this value, that's those two bars, they're not the same height. So there's not a conditional independence. And if I marginalize, I look at taking the margins here, so just looking at Y and X, summing over all the Z's. Y and X are independent, pairwise independent. But Y and Z are not. Z and X are independent. Z and Y are not. X and Y are independent, and X and Z are independent. Okay? So independent structure gets very complicated. But a lot of this can be seen with these categorical data with just looking at where are things flat. But you have to be very careful. So in this thing, the fact that I see flat over the whole thing does not imply all of those variates are independently distributed once I have more than two. So I've got that flat, and I've got some conditional independencies, and I don't have some others. I have some marginal independencies, and I don't have some others. Okay? Here's another example where there are no conditional independencies. But look, every pair is independent. So every pair of variables is independent. Condition on any one of them and they stop being independent. This should worry you, right? This is why we worry about experimental design and randomization and so on, not to get caught like this. So when you condition on something, there in fact is a relationship, but unconditionally there wasn't. So some peculiar things can happen. And here I have what I have. I think, well, I have one conditional independence, and that's it. So I've got X and Y independent given Z, that flat and that flat. No other, well, it's the same here, Y and X given Z. No other flat area, no other independent structure. So just looking at these EIkosograms with three-way and then two-way, reveals a lot about the independent structure of categorical variates. Okay? And you could test any of those with a lineup test. Just remember that when you're looking at the three-way, you may have to look at more than one because that certainly would pop out, but is not necessarily showing independence. It's only showing conditional independence. Okay, so these EIkosograms, they are really, really old. They at least go back to the 17th century. Not always by that name, but they go by a variety of names. I prefer to use the Eikosogram sort of exclusively for this thing that really embeds the probability. And it's got one response and everything else is conditioning. So in that sense, it's kind of like a regression model, right? Where you've got one response and a bunch of conditioning variates. So just we talked way back about box plots have an implicit model. These displays of categorical variates have an implicit model. The Eikosogram is this kind of response model built in. Okay. If I don't want that, if there's no sort of preferred response, I want to treat all of these guys individually, I still might want to look at the response models for all of them and the marginal models like we just looked at a minute ago. But there is another way of displaying this stuff that when you are not specifying one as the response, it too has to be done in many, many different ways. And that's called a Mosaic Plot. The Mosaic Plot you'll see in a second is we're just not worried about that being able to detect independence all over the place like we were with the Eikosogram. And a spine plot is a similar thing that mixes a continuous conditioning variate with a categorical vertical variate. So you'll find those in R. So let's look at some of these things. So I'm going to look at just a two-way table, and there's a function called the Mosaic Plot and a function called the spine plot. And here's a Mosaic Plot. And that looks just like an Eikosogram. Right? Many people confuse these as being the same thing. They're not. A Mosaic Plot agrees only with an Eikosogram when there are only two variates. Right? Except there's a separation here, adding some white space between the bars, which weren't in the plots we displayed. Here's a spine plot. Same thing. Also equivalent to an Eikosogram when they've got two variates and it's both variates are categorical. Okay, same thing. Equivalent Eikosogram. Where they differ is when you've got more than two variates. So we've looked at having the response in class and sex together on the Eikosogram versus looking at this for the Mosaic Plot. So here's the Eikosogram. So now I've got three variates. On the left, I have males from here over, crew, third, second, first. Those are the males. They do not survive in blue. They do survive in gray. Females are on the right. So you can see the proportion of females is much smaller, particularly very few crew members that are female. And the largest group of females is third class. The largest group of males is in the crew. So you can see that conditional on sex, it's still not a flat diagram here. You might want to test that, conditional on sex, whether or not there's independence there. Conditional on being female sex, it's definitely very different, right? Far greater proportion of third class died than first class women. Okay. So definitely not the case. Here's the Mosaic Plot. So what the Mosaic Plot does that's different is you notice that I've got survival here, sex here, and inside here I've got the class. So what happens is I split in two, just like I did with the Eikosogram, into male and female. Then I turn it sideways. And I split each one of these. I split the males here between whether they survived or they didn't survive. Then I take the females and split these between whether they survived or they didn't survive. Okay. And now I look at any one of this I do a next step. There's sort of this recursive alternating splitting. take the males that did not survive, and I split those vertically now into the classes. I take the males that did survive, split those into the class, and they no longer line up, right? And same here for females. So it's going to go alternating, go back and forth. So that's a mosaic plot. There's no defined response. It still has this order component. I could have had, you know, a class on the vertical axis that would have looked a little different. So you still have all the variations you had before, but you no longer have everybody lining up with one specified response and many specified categories. So that's a mosaic plot. So again, just look. This is the three-way table with now sex on the vertical axis, as you can see before. There's sex on the vertical axis. For the mosaic plot, it's splitting differently. Okay, does everybody understand mosaic plots? These are by far more commonly used in analysis, particularly if anybody taken stat 431. Okay, so you may may remember log linear models. So this is a natural plot from log linear modeling, right? Where you've got a node identified response. This is a much more natural model, particularly here for a binary response for think like a logistic kind of modeling. Okay, so again, class on the vertical axis, and there it is, mosaic plot. So every one of those is the same data set, just depending on the order in which the variables occur. And as you might guess, the time we spent that, I'm a far bigger proponent of EIkosograms than I am of mosaic plots, just for interpretability. Same information. So, let's see. As the number of conditioning variates become greater, the differences become greater. So there I've got survived, and I've got class, sex, and age. There's the mosaic plot. This one, I have a preference for interpretability, and that's a mosaic plot. Any questions? Okay, that's all I want to say about data visualization for categorical variates for the moment.